largely it has that left hand, right hand kind of, so this pocket is chiral. And I can make this pocket a chiral, and I can make any of your shake hand exercise successful if you were to stick this thumb like this and try to do shake hand. You don't sense the difference between right versus left. It would be a successful shake hand if you don't use your thumb. So thumb plays a vital role in recognizing right hand. The right hand thumb recognizes the other person's right hand thumb. That is where you get the sense of chirality. It is a fit because of use of this right hand. So this plays a vital role. And I am talking about a receptor where I am using this thumb very, very effectively, that this provides the chiral pocket, and if it was flat, any drug molecule, irrespective of its chirality or a chiral molecule, would have fit nicely, and it would have stopped proliferation of a pathogen and so on. So drug molecules are supposed to be binding to biological receptors. It could be a protein, it could be a DNA helical geometry, it could be very many other sites. But imagine the constituents of biological system. What are the major constituents, major building blocks that make biological systems at the residue level? Carbohydrates, inherently chiral. Carbohydrates, inherently chiral, multiple stereogenic centers in it. And what is the other major constituent? Amino acid. And most amino acids are chiral, and amino acids combine through peptidic linkage to make small peptides, and several of these peptides combine together to form enzymes, and this is our target receptor. We want to stop enzymatic action in a pathogen that is extremely important for survival, and I will slowly merge with how DFT can help us understand chiral manifestations in molecular recognition, which is vital to drug discovery programs. Okay, so right hand shake hand. Let's say RR shake hand was successful, which is matched. This is a matched interaction, and right hand, left hand shake hand was not matched, or this is mismatched. This is a mismatched interaction. This is a mismatched interaction which we could feel in a macroscopic sense. Now, I am talking about an enzyme receptor. You are sending a chiral drug which is supposed to effectively bind and stop enzyme activity, and this enzyme is that of the bad element called pathogen. Could be bacterial or viral, amoebic. These enzymes are supposed to be prevented from its action so that we can kill those pathogens. So this is a drug molecule which is supposed to go and dock itself, fit itself very nicely in the so-called receptor site, and here comes whether or not the drug that is sent will be a match interaction, or if the drug that I send is something like this, there is a shape misfit and chirality misfit, it will not be effective. The drug that is used, this drug is chiral, receptor is chiral, but I am using a wrong mismatched entity of the drug, mismatched optical isomer of the drug, so it is not fitting well is still an okay situation because drug is less efficient. That is still okay. But what if this drug binds to some undesired location, not on the pathogen, but on very important enzyme in human system. Very important enzyme in human system, preventing that enzyme's activity or reducing that enzyme's efficacy, leading to undesired impact. So that is why when you use a chiral drug for human systems or animal systems, it is extremely important to realize where it will bind, whether or not it would produce deleterious effect, bad effects on the human system. That is why there is a lot of FDA regulatory compliance, Federal Drug Administration, FDA regulatory compliance is closely connected to match-mismatch analysis of the drug which is supposed to be or which is being suggested as a potential drug against this kind of disease conditions. So there is stringent regulatory compliance. This will be at least double or triple more stricter when your drug being discovered, drug being proposed is chiral. So I am trying to impress upon you the importance of chirality when you are in a drug discovery program. In general, receptors are chiral. The drug used is also chiral. Then you are talking about a match-mismatch problem in the biological system. Match-match is a success story. As long as you send your drug only in optically pure match form, which will perfectly dock to the known site, then it is absolutely fine. But the mismatched one, no, this has gone to sleep. The mismatched one, if mismatched is less effectively fitting or not fitting at the site, it is okay. But the mismatched drug version, mismatched optical isomer, mismatched enantiomer, if it finds a new target which is undesired target, it can produce really bad effect. That is why FDA is very strict on chirality. Now, what is the connection with DFT? For molecular recognition, in general, molecular recognition problems, you can use like one of the things drug companies, pharma companies use very routinely is what is known as a docking. I think there are possibly some discussion on docking, maybe Nishant or somebody, I don't know. So this is a very, very useful tool used in the pipeline of drug discovery. Imagine you have a lead compound or a lead candidate which is a drug, say which looks like this, and you have a receptor which is like this. So I have a receptor to which this drug is supposed to bind, and I can evaluate the docking score, which would be an approximate measure of how well it is fitting, approximate measure of how well this new candidate is likely to fit. This is in silico modeling. In silico modeling, one can get the docking score, but if you want to go more fine-grained, DFT comes handy. DFT comes handy in the sense that if I just zoom out this region, let's say zoom out only this region, I focus on only this region. Let's say I see a aromatic residue protruding out from one of the amino acid residues. It could be a phenylalanine, it could be a tyrosine. There are many amino acids which has aromatic residues. So I'm just zooming out one small region of this large receptor site, which is an enzyme with a predefined shape, which is dynamic, but fluctuation, if you take the average, it largely looks like something like this. That is my receptor site. Now, this is showing a flat region here at this, and this is my guest molecule, which is, let's say, a small molecule potential drug candidate under investigation, and which showed a prospective, promising docking score. So I am now stepping in with my DFT expertise to look at, hey, is this interaction genuine? Is it reliable? Why is it showing a superior docking score compared to its precursor, compared to its similar other analogs. So this is showing a very good docking score. So when I'm scanning region by region, what I found is that this guest molecule over here has a CH group, a methane-like residue. Let's say R group and some R dash group, and there is a CH pointing towards this. So I have all other decorations inside this molecule. But I'm just focusing on one region to realize that there is, so this is where you can do DFT computations on model system, or even that fragment, the fragment that you identified as very close, geometrically closest point, you just expand it, take a look at this, and you see there is a CH dot 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 at the same level as this dash. This is notational preciseness. So this is a CH pi non-covalent interaction. CH pi non-covalent interaction omnipresent in biological receptor guest interaction. Omnipresent. Omnipresent because many of these enzymes will have aromatic residues, and you will see this sort of interaction. This is well within the reach of dispersion corrected DFT, density functional theory computation. You can do it on model system, and DFT being relatively cheaper compared to wave function analogs, you can do even a larger system. You might want to do a QM-MM kind of study where the focus region, such as this inner lining and this region, may be treated with DFT. Dispersion corrected DFT can reasonably well capture this sort of non-covalent interaction. So what I am saying is the utility of DFT goes all the way to drug discovery, which would help ensure that human life on Earth survives and sustains for longer period. And there is a reason for bringing up this sort of point of view, is that if you look at origin of life, if you look at small organisms and more evolved, sophisticated entities like, or species like humans, whom do you think is more senior on the face of the earth? Who is more senior, who had lived much longer than humans? Who is pathogens? Bacteria, single cell organisms. All these smaller entities, they have been here on earth well before we have any evidence of human activity. So humans are much more junior to these pathogens. And pathogens in a 24-hour human clock, 24-hour, they proliferate n generations within that 24-hour. And we take our life expectancy is maybe 75 in India. So if you look at a generation, maximum 3 generations can coexist, maybe 4 in rare cases. And that's all human generational gap is. In about 200 years, maybe 4 to 5 generations. But in 24 hours, more than 100 generations of bacteria evolved. To summarize, this evolutionary advantage of bacteria is such that they can always adapt to changing environment, always adapt to the kind of adversaries humans present to them, such as drugs, such as antibiotic. So humans will always be in a constant battle with these seniors to survive. And that is why, as long as humans live, new drugs and discovery of new drugs is unavoidable, perpetual activity. Older drugs may not work in few years. There are classic examples of multi-drug resistant antibiotic. There are numerous examples. The drugs which were in use 30 years ago no longer in use today because it is no more effective. It happens to agriculture again. The pathogens which will attack crops, which will reduce the efficiency of crop production. If it impacts rice and wheat, imagine what would happen to our food supply chain. Rice and wheat badly affected. It had happened in a big way in cotton farms in Maharashtra. Cotton farms, the natural cotton which is used for making clothes, the cotton was badly impacted by pathogenic activity. Crop production reduced to such a level that immediate and serious interventions were required. So pathogens are smart. smarter than us any day they are smarter than us. Okay, so we have to develop immunity in one way. We have to use drugs to survive. We have to discover new drugs to survive. And in that drug discovery pipeline, your dispersion corrected DFT aided by molecular docking studies play an important role in the entire drug discovery process. This is one major applications of DFT, that you can evaluate what is the responsible factor making this particular lead compound bind better, and perhaps it will show superior activity when it is taken all the way to in vivo, in vitro studies and so on. So this is one intervention where DFT can help you understand geometry, nature of interaction, how the position orientation of this drug with respect to the receptor is changing. So all these are useful in extracting molecular level understanding in drug discovery. Very complex receptor guest interaction, you can apply DFT methods to look at this interaction in its fine grained manner, almost going to the atomistic level, looking at each interaction. Now, if you look at this interaction in isolation, anyone wants to make a guess how weak this, imagine a prototype. I have a benzene, okay, I have a benzene, I have methane. I have methane CH4. So if I try to locate a minimum energy, ground state minimum energy complex between benzene and methane, anyone wants to comment what would be the interaction energy possible, which can be calculated by computations as energy of this complex minus sum of energies of separated benzene and methane. That is how you estimate the binding energy of methane to benzene by using what is known as a super system approach or a complexation energy approach, where the complex energy minus sum of individual energies will give you the strength of binding. So any guess on what would be this binding energy approximately? Anybody? It will be weak, strong? Weak or strong? Weak. And if it is weak, less than 5 kcal, more than 10 kcal. How many for less than 5 kcal? How many people? You have not taken breakfast? Hands are like, huh? How many for less than 5 kcal? Okay. How many for less than 2 kcal? That is almost 2 only. 2 response, 4 response. Okay. So how many for less than 1 kcal? Okay, 1 person for less than 1 kcal. This would be somewhere in that range. 1 CH pi is around less than 2 kcal definitely. It's a weak interaction. But now imagine this guy has 1 CH pi interaction here, 1 here, 1 here, 1 here. Although not linearly and additive, 4 CH pi can make the binding energy something like 5 kcal, which is reasonable. And I also want to tell you one thing which is very important in life, that is attachment with detachment. Attachment with detachment. So what is the meaning here? If this drug binds permanently and forms a covalent bond, it is not always desirable to have a reactive interaction between the receptor and the drug. Reactive interaction is not very much required in many situations. Some of these reactions can produce free radical that can lead to collateral damages and so on. So most often it is non-covalent interaction that induces drug target interactions. So many a times it is weak interactions of this kind which will help you find a better binder, and this better binder is giving a hope that it could potentially be a drug of tomorrow. So this is one use case scenario of DFT computation where you are looking at molecular recognition by fine-grained analysis of what are the nature and type of interaction that will help you create a drug molecule. If I found 4 CH pi interaction and no other interaction, just for hypothetical discussion point of view, if I found 4 CH pi interaction contributed by this the incoming guest molecule, maybe I want to enhance, capitalize, I want to revise my strategy and provide more CH pi donors, because this inner lining of the receptor is decorated with so many aromatic residues? And if so, I just want to bang on CH pi interaction as a lead to finding more effective binders to prevent proliferation due to this enzyme. So I am looking at a molecularly informed design strategy because I found the best binder, best guest molecule, best potential drug candidate shows 4 CH pi interactions, and I want to make it 5 or 7. That may be adding to the engineering of how you design small candidate, small molecule, which is size-wise very similar because you cannot expand, you cannot change anything on the receptor, you can only play around with the guest molecule which we are working on. So in silico modeling would typically use a lot of these concepts to be able to discover new candidate which will fit nicely, but it will also enhance non-covalent interaction with the receptor, and this is one of the applications of using DFT for molecular recognition because DFT is cheap to do, cheaper computationally to do, you can evaluate these interactions. That is one useful situation where DFT is widely applied. Are there any questions? Yes. Yeah. So if you look at the full complex system, it may not be easy to optimize. So typically you freeze the receptor, so you don't allow dynamics or you don't allow the receptor to undergo any geometric change. You have a frozen geometry of the receptor, and typically some of these receptor geometries are obtained from protein crystallography. So you have the static picture of the receptor site, which will give us a very good idea about the cavity size, shape. Size and shape plays a very, very important role in considering this family of drug molecule or that family of drug molecule. If this is more planar and if I have a receptor site which is like this, I may consider this sort of molecule. But receptor site is like this would like just dangle around, would not fit well. So I may consider another family of candidates to find the best fit. So to answer you, you have a frozen geometry of the receptor learned from crystallography or NMR method, which is able to capture somewhat the dynamical aspect, but this guest molecule, which is our potential drug candidate, is docked in to get the first estimate whether or not it is fitting shape-wise and size-wise. That is the first consideration. And once it is identified as fitting shape and size-wise, then you look at the fine-grained interactions, fine-grained details of what are the interactions that is holding them at that receptor site. So to answer you, your guest molecule can be optimized, but you would not look for a gradient of minimum energy configuration of this entire complex because target is very big. Typically it is very big. But you can always look at, if you found geometric proximity at 4 different locations, that is due to aromatic residue, then for each of those locations you can develop independent model systems by truncation, look at that model system and evaluate CH pi interactions at 4 different locations, put them together to develop more molecularly informed design strategy for which this model system calculation can be used. Any other questions? Yes. Yes. Yeah. Correct. Yes.
So when you're doing docking, either using Schrodinger or you're doing auto-dock,
Yes. Yeah.
it gives some kind of binding energy and it gives that binding packet. Candidate will go on to bind with the binding energy. When we mimic with the DFT, we cannot go for 3000 amino acids.
Absolutely. Yeah. Right.
So when we are taking only the binding packet particular amino acids which are very close and interacting with the molecule, then binding energy may differ.
Yes.
And we are able to mimic only the active bonding. And several other interactions are we are not able to do that part. And when we go for the publications or the matter, there are a lot of comments. So how you are, because it's come almost -7 in the docking or -8 in the docking. When you go to dock, DFT will give almost 30 to 40 minus.
Yeah.
So how can another thing when we are another thing we are supporting with the quantum of calculations also by checking the almost 100 mole. will be taking less, and that one will go for DFT. But the questions comes, we are not able to match exactly what we are, and we are trying to give the information about the engine modeling information, not more than that. That's what we are clearly writing in the paper. But your comments are totally different. So how you are matching with the docking with the DFT, because you are not considering that again they are coming and finding out the number of amino acids.
Yeah. So these are two different tools with the granularity that docking can give versus what DFT can give is entirely different. So here my purpose of saying the docking is a method to know the size and shape fit first, and it has its own scoring, and you are comparing docking which are done with its own limitations but over a series of compounds. So within that closed group of compounds, the difference between compound A and compound A dash is more reliable than compound A and compound B, which is B is very different for maybe another receptor site or a different modification of receptor site. So it has its own utility, but DFT definitely it cannot be done on such big systems. You may at best can do a QMMM if that is allowed, that is computationally permissible. But the other option is to look at, as you said, residue-wise interaction. And that is a very effective strategy. Residue-wise interaction will give you a partial picture. Like, any computation would have the issue of the parable of blind persons inspecting elephant and reporting. Okay, any sort of computation, it is good at each of those persons reported that elephant looks like or feels like this is true. From their inspection, it is true. But when you superimpose all of that, it becomes more true for a person who had seen elephant in its totality. Correct? But each of those computations bring something true, locally relevant with whatever granularity, but when you try to put them together, it gives a more complete picture. So that limitations would remain. So the residue wise, in my personal opinion is that the DFT computed interaction energy is not to be compared with docking score, because they are entirely different technique. One is built upon largely force field. Yeah. Yeah. So there are, having said this, to be fair to that community who develops this, force field based docking, etc. So there are many refinements such as polarizable force field, inclusion of solvent effects, and adding some sort of a charge Drude oscillator type of systems. There are a lot of developments happening in force field to address situations which are well beyond hydrogen bonding as a key interaction. The pi-pi interaction, I wouldn't prefer to call it pi stacking, because I'm against the use of pi stacking. We can discuss in the tea time why I don't like pi stacking. So pi-pi interaction is another thing, CH-pi is another thing. And there are many such weak interactions which are not within the purview of force field, standard force field, but people are trying to refine force field so that this sort of use cases would become improved. So there was one more question here, then I will move on. Yes, yeah. Okay. Then we can save time. We can. Oh, yeah. Very good question. So, see, it is an averaging. This can be regarded as just a fluctuation also. But when you talk about difference between two such thermally disordered systems, the difference is more reliable than absolute numbers. So one interaction as such cannot be relied upon heavily, but several interaction in situation 1, several interactions, similar interaction in situation 2, that difference is more reliable. That is always the case with the difference between two electronic structure energies. Like if you look at bond dissociation of a OH bond. Bond dissociation of OH bond, RCOH and proton. So when you look at problems like this, you are measuring the weight of captain of a ship. First by weighing the ship plus captain, then download the captain and reweigh the ship. That's what is happening. There's always that challenge which will remain, but differences are more reliable, and that is where I started off with this chiral recognition, because I want to get into how we have used this difference as the central control element to regulate what an enantiomer will be produced in a catalytic reaction. That is why I am setting all this stage, because yesterday I promised that I will present you some examples where DFT has been used ahead of experiments, followed by experimental validation. That was a promise I gave yesterday evening, that DFT is very powerful tool to rationalize experimental observation. This is a large application domain. Rationalization of experimental observations. This is where people with DFT skill sets are highly sought after by experimental chemists. They are always in demand. Experimental chemists will approach you, hey, can you do a DFT computation so that I can publish a better paper? Not necessarily to understand their own chemistry, but to publish a better paper. Okay, so but that being a reality, you cannot really avoid this statement, and I don't want to say right, wrong, superior, inferior debate. I don't want to get into that. But if the true intent of DFT computation is to find out why things happen the way it happens, if that is a true intent, then that collaboration is fruitful. And I will show some example. That collaboration is fruitful. Whereas, if someone says that I have some nice result, it will go into Journal of Organic Chemistry, but if you do computation, it will go into JSCS. If that is the stated objective, I will, the very first minute, I will take a 2-step behind and say, sorry, bye-bye, I don't want to discuss your science. And the reality is that it is brutally one-sided. There is an interesting experimental observation. They want to rationalize it by using DFT computation, look at the mechanism, look at transition state, comment on catalytic efficiency, major product, various forms of selectivity, all holistic, worthwhile perspective to investigate. But the problem is that I will not read your part of the manuscript. You are the best person, so you take care of it. I will bring my experimental results, and then there is this oil and water type of, you club them together and try to publish a paper so that it can go into JSCS. I don't like that sort of thing. Okay, but that is a reality. You cannot escape certain realities, it will remain. So large part of use of DFT in chemical reactions appear in the form of rationalization of important observations. Why things happen the way it happened. The other part, which is like this is mostly the forward arrow, rationalize experimental observation. So I will write these keywords here. So this is experiment, this is theory, theory should be right below, theory forms the foundation, and then there is connecting these two, computation plays the fusion role between experiment and theory. Theory exists independent of whatever. So there is a strong foundation. If I go to meetings like ICQC, WATOC, APC, TCC, it's a huge gathering. The WATOC last meeting was maybe 1,400 people. And previous editions of WATOC is World Association of Theoretical and Computational Chemists. It is one of the largest bodies, and ICQC, I was supposed to be going to ICQC, but I cancelled that trip. So it is being held in Berkeley later this week. So International Conference on Quantum Chemistry. So largest gathering, these are in excess of 1,000 people. It's not a small community. So theory is very strong globally and very strong in India. And theorists develop new theories, create improved understanding, typically on small molecules, small systems, and some of these are extended to larger assemblies, larger systems. And experimentalists, on the other hand, they work independent of theories. Whenever they require, they would resort to some version of theory to explain what their observations are. And these are if you look at the extent of or overlap integral between these two orbitals and overlap integral between any of these orbitals, you will see very disproportionate share. So theorists do not communicate much and effectively with experimentalists. Experimentalists do not communicate with theorists. And chemistry is still better, but if you go to physics, it is almost watertight compartments. Theoretical physicists would never approve experimental physics as anything worthwhile. They have such a rift, and they don't even I have heard stories from TAFR and other physics departments, they don't even look at each other. They just don't look at each other. At least like 20, 30 years ago, that was the stories prevailing in physics departments. But now, if you try to coalesce all these for benefit of science, then it becomes wonderful. You try to improve overlap integral. That is my career. In my career, I bring computations and improve that overlap integral with both ends, with theory as well as with experimentalists. So I have been, of course, there are challenges in doing that. The biggest challenge is identity crisis. Okay, the theorist would not regard me as a theorist because I am application specialist, and experimentalists would not regard me as an experimentalist because I don't touch flask and chemicals. So what kind of chemist are you? And my response is, I am a chemist. I'm a chemist, and I like computations, and I use theory to compute on experimentally relevant systems. So because that will enable me to rationalize many interesting observations, and from rationalization, I go to the prediction. The prediction ahead of experiment. And I can tell you at the outset, predictions are always hard. And I'm quoting Niels Bohr's statement, predictions are always hard, particularly about the future. Predictions are always hard, particularly about the future. And the entire domain of artificial intelligence is all about predictions. Learn from the past, predict future, right? Learn from past, predict future. So you're starting from IIT Madras campus, going to Chennai airport. Google is predicting how much time it would take with an error of plus or minus, say, 5 minutes, 10 minutes, unless there is an accident or something. It is largely accurate. It's a prediction. It's an assurance that you will reach in 34 minutes. It's a prediction. You're not enacted on that prediction. You're not validating it yet. Prediction is an integral part. Sometimes you come across people in your lives, the very first interaction, you just don't like that person. And your generation, you will say, oh, I was not finding a good vibe. A, you never interacted with that person ever in your life. B, you heard anything about that person, still you say that, oh, I didn't find a good vibe. What are you doing? You're predicting. You're predicting that person would not vibe with you, the person is bad or whatever in your judgment, and later, after 2 years of MSc, you realize that person was indeed bad. So you feel good. Because your prediction got validated. On the other hand, you found a person who rarely looked at you, but you kind of liked him or her. And for boys, it's so common that the very first sight they start liking the opposite gender, which is like way more common than girls liking, but girls may like, but they will not acknowledge. Okay, so no gender thing, but equally applicable in both sides. So you found a person, the vibe is good, you did not talk, but you had an impression which was good. And later, turned out that person was very nice, very good. And you had limited interaction, but your intuition got validated again. By end of 2-year MSc, you found that person is super good, and that is what I told in day one. So your prediction got validated. I can tell you, almost all of science is about predicting and validating your intuition later. Almost all of science, you think of it. Hypothesis. You start with a hypothesis, collect evidence, revise hypothesis, prove or disprove. Where is the source of hypothesis? It's a prediction of some kind, right? You're predicting, validating, predicting, validating. So if you can do a lot of your science by using rationalization as a use case scenario, application of DFT, you can also do it in the reverse way. And when you set out to do computation on a very complex experimental observation, set out to do such computation, You have an intuition, maybe it will work. Maybe there is a paper in the vicinity, maybe I can publish one more paper. There are many of my acquaintances and quote unquote friends. Why is quote unquote friends? In professional world, nobody is a friend. Yeah? Because peer review system is anonymous. What you thought as your good friend will put you down. Because they hide under the shadow of anonymity. So therefore, quote unquote friends, that means in professional circuit, you can find a good friend in a subject orthogonal to yours. You can find a genuine person, subject orthogonal to yours. In professional circuit, it's always difficult to find a genuine friend with whom you can open up, very well. It's very difficult, very difficult. At least my experience. Maybe I am a bad person, so I didn't find anyone who is like quote unquote friend. But then, always it is about prediction, validation. So I will give some examples of how I have undertaken this journey. Numerous papers, numerous studies, numerous projects, many PhDs who rationalized interesting experimental observation. And I should also tell you one life story so that you can get a feel for how passionate I am in pursuing my practice, my pursuance of science. The story was that I went to IIT Bangalore back in 1996 as a timid boy from a small town, Trivandrum, and it's not a big town, not a metro, and our classes used to be held in English, so profs will talk in English, but between us, we always talked in mother tongue. The exams were written in English, so theoretical English is very good, but spoken English is near zero. And I have had a student in my department who came from interior Tamil Nadu, and he did PhD in IIT Bombay, and when he was graduating, he gave a small speech of sharing his experience, which was very nice. He said, I come from a place where even English is taught in Tamil. So I was from a small town, walked into a room with 13 professors from inorganic and physical chemistry department. I knew one or two of them. Those days there is no website, even if there is a website, no photo. So if you have to know someone, you really have to go in person, attend some conferences. So I could recognize 2 people out of 13 people sitting there. I have no idea who is who. All I know is that IIC Prof hai. So must be really big. Okay. So I can barely speak English. I walked into the room. They started asking questions on theoretical, because the first thing they asked, what is your area of interest? I said theoretical chemistry, quantum chemistry. Okay. And then people are looking at each other, started exchanging some smile, because rarely people walk in and say they are interested in theoretical chemistry. So I said theoretical chemistry. They started asking questions, about 20-25 minutes, and I'm just sitting, and there came a question which has to do with, like, they gave a pair of operator and show that it is commuting. So I have to do operator algebra to show that it is commuting with a residue or zero. So I have to kind of write down something, and I didn't know what to say. And I was like, and somebody understood the limitation that maybe I'm struggling with language. He asked, what do you want? I said, can I get a pen? No, you have the board, you can go and write. I was like super happy. Went to the board, showed that it is commuting, and they were happy, and then went on and on. And slowly I gained confidence. Hey, I can talk in English. Oh, I can respond in English. That was an immediate realization. Oh, I can talk in English. Oh, is it so? Okay. So the questions went on and on. Then eventually it went to a question. Benny Cheryl was the person. Later I realized he was Benny Cheryl. Benny Cheryl asked me this question that, hey, next question that we are going to ask you, we don't expect a response from you, but we don't expect an answer from you, but you make an attempt. So what he asked was, are you aware of, and he said, this is the last question, are you aware of any electronic structure theory that has a operator on exponent? I said chapter 7, Ira N. Levin's book has a chapter called coupled cluster theory. Do you mean that? He said, okay, thank you very much. Done. So my interview closed with that question, whether I am aware of anything to do with coupled cluster operator. So I said, this is what it is. So the point I am making is, I had the option of switching entirely to theoretical chemistry. I was selected from IPC, SSU, and organic chemistry. I had to make a career choice. Do I stay connected with real life experiments, or I drift more into the mathematical world of quantum chemistry? And I thought deep and hard. Nobody was consulted. I took a decision that I want to stay in touch with experiments. That is what made me a computational organic chemist. I joined organic chemistry department, not doing any experiments, but doing computations with J. Chandrasekhar. Those who do liquid simulation would know TIP3P water model was a creation by my PhD advisor when he was with Bill Jorgensen as a postdoc. It's one of the very well cited paper, Jeffrey Madura and J. Chandrasekhar. So and then J. Chandrasekhar kept on working as a postdoc with Paul Schleyer, who is another pioneering computational chemist. So I have inherited that tradition of you can rationalize, you get excited because you know why reactions, why the product distribution is the way it got distributed, and I wanted to also use prediction ahead of experiments. Okay, so this is the stage which I have set. How much more time I have? Half an hour? 35 minutes, okay. So now I will enter the world of prediction ahead of experiments. Are there any questions? Any live questions? Pressing questions on why to be a scientist or something? These are some of my public lectures, why to be a scientist. How to read a paper, how to give a talk on a talk. These are public lectures. Any discipline, people would find it useful. Okay, so let me move to the prediction side. I have numerous examples of rationalizing interesting observations. A large part of my career was on the left side, and slowly I have been drifting towards the right side, both from using AI methods and using DFT methods to predict. So I was visiting University of California, Berkeley back in 2015 on a lecture tour to California and Midwest. So I visited this department, gave a talk, and one of the organic chemists, a famous organic chemist, had a sign up to interact with me for 1 hour later in the day. So I went to his office and he said that, oh, me and my students have read your JOC article, which was published a couple of years ago, and coincidentally this was a JOC article. Eventually it had happened to be a JOC article, and my experience with this article, I introduced a term among my colleagues, and wherever I give a lecture I introduce this term. This JOC article was my most uploaded manuscript. You heard of most downloaded manuscript, right? So what is the meaning of most uploaded manuscript? You upload in Nature Communication, DES reject, come back. You upload in JSCS, get DES reject, come back. Upload in Angawande, there is a cultural sequence that one would follow. Yeah. So from every place it was rejected, 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 eventually landed in JOC. And this paper was read by this famous organic chemist and asked me, hey Sunoj, we have a situation, we are not able to improve enantiomer selectivity of this reaction, but the yield of this reaction is very good. So do you think, based on your previous experience in working on a similar problem, would you be interested in taking up this project and help us? And I thought like, oh, UC Berkeley ranked #1 in the world in chemistry. So I was like, okay, sounds interesting, and this is similar to one of the papers which we have published. So I thought, okay, yeah, I'm interested straight away. In 2 minutes I said I'm interested, but I had no idea what I am getting into. There is a saying that, head in first. You heard this? Head in first. Meaning that you don't know what you are getting into, but without realizing, without sensing the trouble, you put your head inside. Okay, it may get chopped also. You may become bald at the end. So I took that head in first policy. I said, yes, we will do it. What is that science? The science is like this, and I will simplify the organic chemistry for you. The science is, there is a new carbon aryl bond formation here in the product, and rest of the things are all same, so you don't look at anywhere except a new bond that is formed. So a product has a new bond between this reactant and this reactant. So A1 is combining with D1 to produce P1. A and D combines to form product P. That's a reaction. But now, as much as Indian marriages, the marriage is just a 2 minutes tying the knot. That's all happens, right? But just for that to happen, as much as enzymes function, enzymes will move around and do all these conformational dynamics before it actually come to the so-called active state, active site, and do some, with all the decoration, what an enzyme will do, just do a deprotonation. Such a shame, right? So many amino acids, eventually to deprotonate an alcohol, and you may call it alcohol dehydrogenase and whatever, all it does is rip off a OH group from an alcohol. And for that, there are thousands of atoms. And this is not just my statement. Rolf Hoffman said this, what a waste of energy. So many atoms to pull out a hydroxyl group. Yeah? So like in Indian marriages, so many events, so many functions, so much money is spent, eventually tie the knot for 2 minutes. Yeah? So this is so natural that we embellish things, we decorate things so much to do some simple transformation. Here is one transformation. So this is a diazonium salt. Those who have forgotten organic chemistry, it's very easy to handle diazonium salts. These are soluble in polar solvents. So you are forming a new CC bond here, but the CC bond formed is that particular center is chiral. So this center is a stereogenic center. So this molecule will have R or S configuration, and I have impressed upon you, these are very important. If it is a drug candidate of tomorrow, you need extremely high optical purity. So you are looking at selective reaction which will produce one enantiomer over the other enantiomer. That is the objective here. Now, as much as I described all the embellishing, all the decorations in a marriage or all what enzymes does, organic chemists also have the habit of putting in too many things into the reaction vessel. And typically what they do, they mix A and D, those are the reactants, expect formation of P as the product, but they don't leave those A and B at peace. They would add a catalyst, they would add a solvent, some additive, or maybe one more additive, maybe one more, two more. And I have examples of that kind, 7 additives in one CH activation reaction, 7 additives. And my students spent locating 3,500 intermediate possible for such mechanistic problem. And then student graduated, got a job, and who cares, right? So all the 3,500 possibilities are resting eternally in some hard disk somewhere. It is not published. But it is so exotic, so crazy, that how many additives are added, each one would have a role to play. And that is what we do. That's the science that we do. We try to account for, hey, what the hell is this sodium bicarbonate doing? What is its role? Unless we are clear of the mechanism, we cannot do any predictive science. You have to be really, really clear of the mechanism. So let's look at what are the complications here. So there is a catalyst called palladium. It's in palladium 0 state. And there is a chiral catalyst, which is another catalyst. Okay, gone are the days when you would use one catalyst for one reaction. There are 2 catalysts in one pot. One pot means you don't separate anything. You add, there is this, I'm sure many of you would have taken a mojito or whatever in bar. Like they will have a tuk 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 tuk. Huh? You've heard that sound? Tuk tuk tuk. So this is one of those tuk tuk tuk. 2 catalysts, 2 substrate, and a base solvent added, shake it up, get the product. But then each one would have to play some role, right? Some chemically relevant role. So when you look at this, so that was our task to establish. The storyline is that they had only 35% enantio selectivity, which is very bad. Actually, you would put a towel on your head and walk through the corridor in organic chemistry department if you have 34% enantiomeric access. You will not tell anyone. You will not tell anyone unless you have hit 95 and above. Unless you have 90 and above E, you don't say that you did the reaction. So that is the brushing under the carpet, so-called failed reactions. Failed reactions are brushed under the carpet. Even the advisors will not know. The student is ashamed of telling. That's a culture. It's a non-reporting bias. Reporting bias and the bias against reporting because it's poor, 34% E, and that was the time there is a ray of hope manifested from Mumbai to Berkeley and it was me who walked into his office with 34% EE. Hey, Sunoj, can you help us improve the 34% EE? And I put my head and said, yes, we can. And those days, Barack Obama was in power, so I naturally followed his accent, yes, we can. So I was in deep trouble. Someone who is like known for DFT computations on complex catalytic problems said yes. And maybe they are like, when I walked out of his office, he would have said, yeah, I trapped one more guy. I don't know. I thought, yeah, it's a cool stuff. So let us therefore look at the so-called mechanistic cycle. And here, of course, it looks complex, but this is one among several alternatives which one would have to typically consider. That's why it is a pain. It's a lot of work. Like it goes for a couple of years to say the least. There are numerous possibilities, which will encounter what? Because all are added at once. Chemically, there are numerous possibilities. The sodium bicarbonate, for example, sodium carbonate, which is used as a base, and then tuck. What is that base doing? And obviously there is an acid, therefore base will react with acid. So what is that acid? This is that phosphoric acid in the medium. Phosphoric acid will get deprotonated, and then one would say, oh, you don't have to do a computation to say that acid-base reaction will take place. Yeah, I don't have to do a computation. But what is important here is that once the sodium carbonate abstracts the proton, it becomes sodium bicarbonate. And what would be the typical approach? Sodium bicarbonate, who cares? Now, my acid is now deprotonated, acid will act as a ligand, etc., etc. There are numerous modes of participation. Bicarbonate people would just ignore. We don't. Because we like our work. We want to understand if something is produced in situ, bicarbonate is produced in situ, maybe it will have a role. That is where sometimes my students will say that, sir, with half the work that we do, people publish more papers. With half the work that we do on very similar system, people publish more papers. And I respond by saying, paper is a byproduct, PhD is a side product. The skill, that knowledge that you gain is the permanent asset. Skill and knowledge that you have during PhD, gathered during PhD, is the permanent long-term asset for you, not the paper. Paper is good up to what? Getting shortlisted for next step. It's not good beyond that. If you are applying for a faculty position, more paper is dangerous. Why is it dangerous? And I will not elaborate because, anyway. So, optimal number of paper is good only up to shortlisting. Then, how much you know matters, because you will be interviewed. Yeah, you will be asked questions. All those papers no one would remember, because it was good up to shortlisting, and then when questions are asked, it is only your knowledge that will matter, and you will make the cut, you get selected. If you are not knowledgeable, you don't get selected. And papers will do no good. It will do good up to shortlisting, but the true substance is tested in interview. True substance comes out in conversation. The knowledge and scholarship gets reflected in what you say, how you look at things, how you respond to a given scenario. So coming back, I'm sorry, I'm telling too many stories because that's what I'm notorious for. And there was once a course evaluation. At the end of the course, people write course evaluation, students write course evaluation. So in freshman BTech first year, 360 students in the class, very big class. And that year I got a fantastic course evaluation remark. That was, sir should tell less stories and teach more. I thought that was very, very fascinating input. So let me turn back to the story. So there is a sodium bicarbonate produced, and we consider role of sodium bicarbonate, its association with each of the species that is formed. Yesterday's I1, I2, I3, we don't allow sodium bicarbonate to go away based on a very simple physical organic principle. Look at what is the solvent used. Toluene and an ether, low dielectric solvent. Toluene and ether, it is not conducive for polar species to diffuse away. They will stay where they are produced. So sodium carbonate's primary role was to deprotonate the acid. Once it deprotonates, it remains as sodium bicarbonate, and it is unlikely to diffuse away. It will stay stuck because all the species which which are there in the subsequent steps in the mechanism, let's say I1, I2, I3, they are more polar. So bicarbonate has no reason to diffuse away, it will stay stuck, stay somewhere in the vicinity, and we found that sodium bicarbonate is an integral part. I'm just talking about the mechanism. Explicit consideration of sodium bicarbonate in the entire mechanistic steps, that is, in general, I1, I2, I3 all have association with sodium bicarbonate. It has an energetic advantage as opposed to removal of sodium bicarbonate, which will lead to energetic disadvantage. This is one mechanistic intervention. So we consider them because what are we getting into? We are supposed to address that 34% enantiomer selectivity. Why is it 34%? Why is it a failed attempt to induce enantiomer selectivity? And we found there is a free energy advantage for inclusion of sodium bicarbonate in the mechanism. So then what we did, we asked them to redo the experiments by taking out sodium carbonate, because that is the source of bicarbonate. Asked them to use some organic base for deprotonation of phosphoric acid, and when they did the experiment with no sodium carbonate, the yield dropped down to 7%. So reaction was otherwise quantitative. So sodium bicarbonate in this mechanism plays an important role. So we extended that. Of course, this is the energy profile diagram, which I would just skip past. I'm presenting the first critical transition state, which gives you a ray of hope that you are beginning to understand why this is 34% EE, why this is unable to induce high degree of enantiomer selectivity is because of very small energy difference between two competing transition states of same stoichiometry differing in a few of weak interactions. And your earlier question becomes more valid because it's a weak interactions, energy difference is so small, and if I talk to a bunch of theoretical chemists, they will start laughing at me. Yeah, 0.2, 0.5 kcal energy difference, is it trustworthy? No, not at all trustworthy. But we have a handle. This is among several mechanistic alternatives. This is the transition state for migratory insertion, which is responsible for enantiomer selectivity. This is the best estimate we could get from among 30 or 35 different alternatives. Chemically different alternatives. The energy difference turned out to be very small, and it is in very close agreement with the one and only one experimentally known value of that infamous 34% EE. So that 34% originates from nearly degenerate competing transition state. This would have led to R product, this would have led to the S enantiomer. That difference is so minuscule that you have a problem of low EE. So what am I saying? I'm saying that now we seem to have understood, I'm using my words carefully because I'm giving excessive reliance on a very small energy difference, so I should be very, very careful. Of course, as part of calibration process, we would do half a dozen different density functionals, half a dozen different basis sets. So these are all part of supplementary file, which is not of interest for a public discussion. Now one can look up the supplementary to see that they are internally mutually consistent. These competing transition states which control selectivity has very little energy difference. And here is the origin of low selectivity. Here is the one which bothers them. If mechanistically it is a better model, these energy differences are, in a relative sense, these energy differences are reliable, and more than anything, we have now calibrated our transition state against one and only one known experimental number, that is 34 versus predicted 37. This was a day of joy in the lab that we got this number. This was the only number known to us, only number shared with us, and we got the problem nailed down, and we said that looks good, looks good. We sent an interim report, said that your 34%, we now know. Why is it 34%? You look at the weak interactions which are there are very little differences in the weak interaction. More than anything, if I may bring your attention to two weak interactions of the kind which I started with, the CH pi as shown here in the broader context. So there is a CH pi interaction between the substrate and the catalyst, and there is a lone pair pi interaction between the substrate and the catalyst. So here the catalyst, this is a chiral phosphoric acid, catalyst has this, the protruding arms like one of those Shah Rukh Khan poses. Shah Rukh Khan will do this, like the protruding arms of the catalyst, which is the channel for communication, which is the handle for establishing interaction with the substrate where the reaction happened. So this is conceptually very important to understand. The matched version of this transition state, where the catalyst and developing chirality is in a right-hand match form. So there is an effective communication between the arms of the chiral catalyst and the substrate, and this communication channel is opened up in the form of weak interaction. So we thought we will try to fine-tune this weak interaction. Having aided by this knowledge, can we fine-tune this weak interaction? So the catalyst arm is now changed. Instead of a biphenyl, we put this CH3s, and when we introduce these substituents, re-optimize the transition states, our intent was just to play around with the weak interaction, because we found a few and we wanted to see, can we regulate, can we change this weak interaction just to play around with this weak interaction. There were no such plans beyond that 34%, except to remind you of the initial initial interest that I have expressed, that we would be interested in looking at the mechanism. Perhaps we will be able to help you improve the EE. And how do you improve the EE? Design new catalysts, having understood the limitation of the existing catalyst. So we kept on modifying the catalyst purely using DFT computation, dispersion corrected DFT computations. We kept on looking at the transition state, kept on looking at the energy difference between competing TSS, and there came situations where we could improve the EE. For example, this transition state, where we have introduced an adamantyl group. Now it can donate 3 CH as donors to interact with the substrate. So what are we doing? We are just fine-tuning weak interactions in the transition state. I underline weak interactions in the transition state. You know that transition state has an exponential energy dependency. If there is a small change, you remember the values which we talked about, 0.2, 0.5 kcal, very weak but coexisting in tandem. Many of them can perhaps make a difference. And here what are we interested in? We wanted to enhance the difference between these competing transition state, the one which will give you R product, the one which will give you S product. We want to enhance the difference. So we are looking at a difference in energy problem and trying to map the responsible weak interactions that may be contributing to weak interaction. Responsible weak interaction that may be contributing to the energy difference. So what I am saying is, the energy difference can be further rationalized. Energy difference can be further rationalized by analyzing transition states. This is a huge empowerment. First of all, experimentally you cannot access transition state. Now we can see the interactions in a transition state, quite empowering. And with that, we should be able to fine-tune the outcome of the reaction. So what we find, better interaction, a lot of those CH pi's are coming here, CH pi interaction are coming here. The energy difference has improved. The predicted E is now 88%. From 34 to 84 is time to celebrate. And how are you sure that this was just DFT computation? So then what we did, we sent them this slide. We send them this slide. This slide has no predicted enantiomer selectivity. We send them this slide. Hey, can you make, and I was very timid, I should acknowledge, I should confess that I was very timid in sending, not because of fear of failure of our prediction. We knew the EE numbers. We did not tell them. If you tell them, why in the world they would try to do another experiment with a predicted EE of 2%. We started our story from 34%, and we have some examples, 2%, 8%. Why would they do? So deliberately we did not tell them, hey, please do this reaction because I want some calibration of very low EE also as well, and some very high EE. So we send these catalysts. The confession is that I was timid in sending. My timidity is not due to any other factor, but cutting a sorry face as an organic chemist, would this be ever made? These catalysts are non-existing. So I am suggesting, hey, if you were to use this catalyst, you will get a better EE. It is like telling you to buy a Ferrari and then go to airport. I don't know the synthetic challenges in, like you can check up, of course, you can do a retrosynthesis, you can check up available catalog, but they had to make these catalysts. They made this catalyst. That is the beauty, and that's precisely, I respect these, some of these, the Western chaps, the white skin guys, they're like very daring. They want to do, and they will do. They don't look at just from benefit point of view. And I could not, unfortunately, convince any of my countrymen to do validation of my prediction. Because A, they don't take me seriously. No, you're a DFT guy. We don't care. Because you're not an organic chemist. And B, they think that idea came from me, so they're not interested in that. I don't know. It's very weird. So, but these people were willing to make this catalyst. It's not easy. Not easy to make this catalyst. They made this catalyst optically refined, purified, because when you do asymmetric catalysis, you can use only one optically pure catalyst at a time. So they purified, they did those reactions, so kind, so nice, this did those reactions, and now this is a summary table where these entries were filled simultaneously. We do not know each other's value. They send us the chiral HPLC profile, we calculate the experimental EE, all these predictions were done first. And there is a story associated with this paper also. We have collaborated on asymmetric counter-ion directed catalysis in a previous Angawande paper where it was 3.5 pages of experimental results, half a page of our computation, which took 2+ years, but only half a page in the print form. So there was a previous paper, precursor to this paper, which was 3.5 pages of experiment and half page of computation. I usually hate this separate subheading, computational studies. And then they put this 2 years of effort packed into half a page. I did not like that. And in this paper, 9 pages of computation and half a page of experiment. Because experiments came later. These entries, computed entries were filled first and experiments were done over several weeks, which came later. So what is the take-home message? Is that time has come where you can predict ahead of experiment, provided you know mechanistic understanding. You have to have real, genuine mechanistic understanding, then you can drive in the reverse direction as well. The mechanism is non-trivial task, but if you are willing to take the plunge, then there is finite possibility that predictions are realistic. I have many more, I don't have time, but at the same time, if you ask me, hey Sunoj, all your predictions always worked, I would say, as much as uncertainties in life is uncertain, right? It's all about expecting future. Any expectation on future, that is why we use the word expectation. Expectation is closely associated with probability. Expectation always comes with its own uncertainty. So all predictions will have its own error, its own uncertainty, so is life. Now, so there are many, many successful examples, but there was one collaborative work with an Israeli group where we had predicted 28 instances in chiral N-heterocyclic catalysis, 28 instances were in near quantitative match, but there were 2 instances where our predictions were exactly opposite of the experiment. This happened about 6-7 years ago. Even today the paper is not published, not because of the mismatch, because we were unable to find a reason for the mismatch. Mismatch we are willing to disclose, willing to discuss, but we are not able to find why is there a mismatch, and that paper is stalled forever, which is unfortunate. This is only one story which I have where I had a serious disagreement with experimental observation. They redid the experiment. Even in this story there are some cases where they had to redo the experiment not to match quantitatively, but we predicted the enantiomer as R, they got it S. And they had to repeat the experiment by admitting that their catalyst was optically impure, so they had to do additional distillation, extracted the pure catalyst and redid the experiment such that it matched with our prediction. So look at the power of computation. We made them do the experiment, A. We made them repeat the experiment, B. Wow, such a great feeling, right? Like, yeah. Yes, yes, yeah. Yeah, very. Yes, yeah. Very true. Yeah, very true, very true. So I have a AI paper, I can just give you, it's a chem science paper, AI driven predictions followed by experimental validation. There in that story, we are brutally honest in telling that AI is great, but it can never surpass human ingenuity, human knowledge. It will compete with human knowledge at some point of time. We had done AI-based prediction. My experimental collaborator from Scripps Research Institute ranked #1 in organic chemistry at some point of time. And I'm proudly saying that, I kind of collaborate with best of the organic departments in the US and in Israel, but unfortunately not much within our country. Within our country, I did a lot of work in this space, rationalize. They want to publish papers, right? They want to publish in JACS and Gawande. So I'm okay in helping as long as they listen to what we found. So those people who listen to what we found, mechanistic interpretation, I continue to collaborate. But the reverse prediction followed by experiments are typically done with US counterparts. They're willing to do those experiments. And in this AI paper, it's published in Chemical Sciences. It was reaching most uploaded manuscript, but fortunately, Chem Science accepted it. All the ambitious venues like Nature, Communication, JSCS, got kicked left and right, because I was very open in saying that, hey, AI cannot actually deliver unless there is a human in the loop. The human had rejected many of the AI predictions. Hey, this catalyst would work, that catalyst would work, and AI predicted with such high confidence. The human looked at it. Famous organic chemist Ching-Kuang Yu from Scripps Research Institute in California, he looked at it, hey Sunoj, this will take us 6-7 steps and a few weeks to make. Do you want me to make? I said no, but I want your voice to be recorded so that we can publish that. It will take 6-7 steps and few more weeks to make. Is it worth making? My response is no, it's not worth making. So we have stated in as many words that there are several designed AI generated catalysts which we did not make because of synthetic complexity that it would encounter, and we did not make. And the story goes on in brutally assaulting AI-driven prediction. The paper is about showing prospect of AI-driven prediction. But acknowledging failure, we did acknowledge a lot of failure, that some reactions, catalyst predicted, synthesized the catalyst. So this is generative AI application. Generative AI means such molecules do not exist. So you have to make them and then do the chemistry with it. So they made those catalysts. They did the chemistry, and one interesting instance, they made the catalyst, did the chemistry. All you see is the fish in fish tank. They will emit bubbles, right? So all you see is CO2 elimination, no product. Fantastic. AI is so confident, oh, this catalyst will yield you 99% EE, but all it could do was to bubble carbon dioxide. No product. Fantastic. We said that. It's a fun read if you read that paper. Chemical Science, you search Chemical Science generative AI paper from us. So we are very, very honest in telling what we find. We acknowledge our failures, but it's a lot of fun to play with this transition state. There are many, many examples. These are back in the days. A referee had ridiculed us for talking about some weak interaction called CHO interaction. If Professor Desiraju hear this, he will be very annoyed and angry. We talked about CHO interaction in this particular example. One referee ridiculed us. It's not worth talking about CHO interaction. So I don't trust your prediction. And we predicted, put it in literature, 2007, early career. You get kicked from all journals because you're not known outside. So this is one such kicked. OBC is a good journal. That's my last resort. I stopped there. If I couldn't publish in OBC, that means I'm not publishing. I will leave there. I don't go anything beyond OBC. 2 years later, a group from London, Imperial College London, had validated what we said. This is even more fantastic. This is not a collaboration. Independent scientists, independent work, which validated what we predicted. And these are all Nobel Prize stuff, proline catalyzed reaction. Ben List, Macmillan got Nobel Prize for this reaction. If you remember, yesterday I talked about right problem identification at the right time. This was my early career example where we were bold enough to predict what would happen if we were to use bicyclic proline for asymmetric aldol reaction. It got validated and it further got cited positively in many, many papers. So it is a nice journey of being able to rationalize and use that as a platform for prediction, and then nudge experimentalists to do those reactions in wet lab. And actually, when these predictions come, my inner palms are very sweaty because I'm anxious to see the numbers. I don't know the numbers yet. I know my numbers, predicted numbers. And these days we have online meeting where we share tables where our values are not entered, their values are not entered. And minute by minute, they enter their value, we enter our value. In next row, we enter our value, wait for them to enter their value. And those times, I am like super nervous. Oh, how good. And as it progresses, row by row, and I'm like, yes, 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 go ahead. And there will be one mismatch. Oh, okay. Yeah, fine. Next. Oh, yes, again. So if you go back to this, you can see my excitement. Go back to this table. Yeah, so this table, imagine live filling of these tables last 2 columns, and you're waiting for an absolute disaster here. Energy difference would be, way less than thermal fluctuation, not reliable at all. I acknowledge, I admit, poor man's DFT is doing wonders here. Very, very small energy difference, could be due to many things. But when you do the experimental validation, it cannot give high EE. At least that is a good take home. And look at this number. We did not tell them that it is predicted 32. We did not tell them. Why would they do the experiment then? 14% experimentally. And they would be equally disappointed, but for us it's a pleasure that we could make them do a low E reaction and moderate E, poor experimental. Look at high E, 89 predicted, 81. 88 predicted, 84 experimental. This is real fun. You're driving new experiments, providing new direction, rationally found, and that gives a superior joy. And that is one of those applications which I thought I should share with you, that applications of DFT in addressing real, complex, asymmetric catalysis example that defined my career so far. Thank you very much. If you have questions, I'll be happy to take. So the energy difference between transition states which are competing, one would lead to S versus one will lead to R. So you can take a Boltzmann distribution. So this will help you appreciate. Yeah, so you're looking at that delta of delta G double dagger between 2 competing TSs, one responsible for one enantiomer, the other TS is responsible for other enantiomer. So when you apply Boltzmann distribution, you can calculate enantio selectivity. So that's how you look at it. So essentially it depends on the energy difference, the free energy difference between these transition states. And experimentally how you measure that, there is something called chiral column high performance liquid chromatography, HPLC. So you have a stationary phase which is loaded with chiral molecules. So as this chiral product passes through the column, they will have differential handshake, which we had started with. So they will have differential interaction with the stationary phase, and their retention time would be different. So one of the enantiomer will have a preferred interaction with the stationary phase. They will move slower compared to the other enantiomer. So you get nice peaks, and area under the curve is the concentration of these products which are available. So you can determine experimentally like that, and you can use computations to look at energy difference and convert this into a Boltzmann distribution. You can calculate theoretical percentage EE.
Again, will it be similar if you calculate the rate constant like K1 divided by K1 plus K2? Suppose you will apply the RNS equation.
In this case, it should be in principle, but rate constants would come with its own further layers and layers of uncertainty, because we are dealing with the harmonic oscillator approximation to evaluate our free energy. Molecular free energies are calculated by assuming vibrations are harmonic, which is questionable. Okay, but here we are looking at stoichiometrically similar to transition states on whom harmonic approximation is applied. So it is slightly better than looking at absolute rate constant and relying on just the barrier of one step. So we are looking at same step, but stereochemically it is like this versus this. That's a key difference. But they are stoichiometrically similar. So I have issues in getting my vibrational entropy correctly because I'm assuming harmonic oscillator. That is one challenge. Second, solvation effects are typically, in this case, this is toluene example that I described, is using continuum solvation. So there may be some error due to that. So I am willing to live with a bunch of errors, bunch of approximation, as long as I stick to energy difference as my guiding principle, not absolute barriers or rate constants.
Thank you, sir.
Say Boltzmann distribution depends on a specific temperature. Now, if you change the temperature, first of all, your calculation is zero temperature calculation. There is no temperature.
I add thermal correction to
in quantum mechanical stuff. Now, if I change the temperature, in principle, your Boltzmann distribution will change.
Yeah.
But experimentally, can I tell that the enantiomeric excess also will change if I say increase the temperature, concentration of one of these species will go
experimentally,
high.
It's a...
Is it temperature dependent in that exponential as Boltzmann gives, says in the Boltzmann sense?
Yeah, experimentally, the conventional wisdom, textbook wisdom is that lower temperature are preferred for high enantioselectivity.
My question is not that. The Boltzmann distribution, if you want to apply at a given temperature, I know that if we increase the temperature, let's say higher energy species will be more accessible. So, in that situation, if I change the temperature, so here perhaps you are putting room temperature into the account and you are getting some. It has nothing to do with your theoretical calculation.
No, but you are no. But your
energy gap is same. If you change the temperature, ultimately your enantiomeric excess will change because you are taking only the Boltzmann distribution.
Yeah, so here these are all thermal corrected. Before I take a transition from the so-called 0 Kelvin potential energy of the system, transfer that into the actual Gibbs free energy. So I'm adding multiple correction terms. One is thermal correction, which is corrected for 0 Kelvin to room temperature. That is one layer of correction. Then I add entropy corrections, and before I reach the free energy. So these corrections are part of this calculation.